Let's cover some key skills every economist needs to know. First, automation. Good journals require you to hand over your code in a way that anyone can reproduce it, from raw data to final results. You can't do this in Excel. You need to create code that automates your analysis. Second, I'm going to show you how to make your analysis journal ready. This is not only just about what RAs need to know, but what the economists in charge need to demand. Third, the best economists I know their data. I'm going to show you some step-by-steps before you even attempt to model the data. All right, let's go. In the description, you will find a link to the GitHub page where all the code and data is provided. All we need to do is download it. We'll see that in the folder, we have quarterly and monthly data, and we're going to be working with the stopusingexcel.do file today. Just a reminder that our data includes monthly data for CPI, as well as quarterly data for GDP and the components of consumption. So we want to combine these two data sets and make them both quarterly. I have separate videos on where to find the data and to upload them appropriately. This program file is going to include all the commands that we need to run our code. We can highlight sections of it and run it by pressing this little play button up at the top. Here, all I've done is start some output file, but you can also see I have some options that if you want all the figures in black and white, all you would need to do is comment this in. The first part we're going to look at is uploading monthly data. We're going to upload from the CSV file. Our data starts in 1961, and we're going to format this and tell Stata that we are using a monthly time series. The next thing we're going to do is convert our monthly time series to quarterly by running this section of code, basically saying create a variable called time, which is our quarters, set our time to quarters, and collapse down to quarters. The default in Stata is to do everything as an average. You should be very careful to make sure that an average is appropriate. And in the video on uploading, I talk about making sure that when you have asset prices, for example, you make sure to use the end of period value so that you take the last value of the quarter and not the average. The last step we're going to do is upload our quarterly data and then merge with our monthly data that was converted to quarterly. All right, we've got our data in. We should always double check to make sure this looks good. And we have all our series verified. The first thing that we're going to do is generate a new variable, consumption, which is the sum of its components from the textbook identity. And we're going to do this for both real consumption and nominal consumption. We also want to take our growth rates here or any transformations of the data. So here I have the growth rate of Y, which is my GDP variable, and I've specified that it's the year-over-year growth rate because we're working with quarterly data, which requires us to take the fourth leg. I'm also wanting to do this for inflation, so I take the year-over-year growth rate and the consumer price index. We're also going to want to look at shares of GDP, and in contrast to using real variables for the growth rates, we want to use nominal variables for ratios. The last thing that we want to do is label our variables that we just created because we want to show the actual name of the variables and not the code names we gave them in our file. This is really beneficial in Stata because this metadata will be saved and be able to be used later in our graphs, so we don't have to hard code it every time. Before we do any modeling, the first thing we need to do is visualize our data. One principle that you should follow is that if you dropped your figure on the floor, would someone be able to pick it up and read it? So what does this entail? Well, here's a bit of a checklist. First, it should always have a title and it should describe the figure. So here I want to present the consumption share of GDP, and my title is going to be consumption as a percent of GDP. The second thing to remember, and requires attention to detail, is that the axes are for units. Our y-axis is going to be percent because we're going to be graphing percent of GDP, and our x-axis is time, which is in quarters. So we be specific and say quarters. Make sure not to put variable names on your axes, units only. The other thing is we should always include notes, including data source and range in any transformations if it's not obvious from the figure. We also want to include some options such as getting rid of that ugly Stata blue because you never should be able to tell what software created the figures. And we can also add any reference lines we want. Here I'm adding a horizontal line at 56. So let's take a look at our figure. And you can see here we have the solid line at 56. We have our quarters on our x-axis, our percent on our y-axis. Now here we have the title and notes in the figure. This is great for assignments, but if you're writing a paper, this should definitely, both the title and the notes should be done in LaTeX. The second figure that we're going to examine is a two-axis plot. Why do we do this? Well, we're using a two-way command so that we can graph both the growth rate of GDP and CPI inflation with two different axes. We're going to have the units for CPI inflation on the right axis, which means that we're not going to be able to use the metadata for the names. We're going to want to tell the reader in the legend which axis corresponds to which variable. So here I've hard-coded in the variable names in the legend so that you can see that the CPI is going to be the right axis. Otherwise, it's pretty much straightforward, and we can create our graphs of our year-over-year growth rates. Let's take a moment to look at this graph. Anytime someone puts a graph in front of you, whether it's a presentation or your professor or the first time you've graphed the data, there should be a checklist of things you look for immediately. The first thing you should look for is the relative variability of the two series. Here we can see that our units for GDP growth go from 6 to -4, whereas inflation go from 4 to -2. So we have separate axes, but you can see that GDP is more variable than inflation from this graph. The second thing we should look at is whether or not they're positively, negatively correlated, or coincident. Here we can see that when we have big movements in GDP, inflation tends to fall. Similarly, when GDP increases, inflation also increases. This isn't always the case, and it doesn't seem to be particularly strong all the time. So we would expect the correlation to be weakly positive. The third thing we should look for is the timing of the two variables. This is particularly important when we're interested in forecasting. So for example, we can see that GDP here troughs a couple quarters before inflation. This means it could be particularly useful for forecasting inflation. We can also see it when there's positive movements because GDP is peaking a couple quarters before inflation. This suggests just from the figure that GDP may lead inflation by a couple quarters. The last type of plot that you should always examine is a scatter plot, especially anytime you're going to model two variables or run a regression between two variables. It's really important to see the data in a scatter plot. Here, what we're going to do is create a scatter plot of the growth rate of GDP and inflation, and we're also going to include a line of best fit, so standard OLS regression, and otherwise all the other aspects such as our legends are going to be standard. Here, we see that we have a positive correlation between our GDP growth and our CPI inflation. We also can observe a certain outliers which are going to have a lot of leverage on our regressions. Here we are confirming that we have a positive correlation between the two variables, which means we should have priors on the parameters even before we estimate our model. When you're shown a graph, the first things you should look for are the relative variability of the data, if they're positively or negatively correlated, and if there's any leading or lagging relationships. This is a cheat sheet to basically show you how to calculate these summary statistics in the data so you can quantify this precisely. For variability, we can look at the relative variability by taking the ratio of the standard deviations of the two variables. For example, the standard deviation of CPI inflation would be less variable than the standard deviation of GDP if this ratio is less than 1. If it is more variable, then the ratio should be greater than 1. Similarly, when trying to determine whether something is pro-cyclical or counter-cyclical, we can just look at the contemporaneous correlations of our two variables. Here, if we have a positive correlation, they're pro-cyclical, negative correlation would be counter-cyclical, and if the correlation is indistinguishable from 0, we would say it's acyclical. The last thing is to look at the correlations with the lag of one variable with the contemporaneous movement in the other variable. If we take the correlation of, say, previous quarter's CPI inflation with current GDP, and this is our largest correlation, then this would say X peaks before Y. Similarly, if we look at the future value of CPI and the correlation with contemporaneous GDP, and this is our largest correlation, we can confirm that CPI lags GDP. In section 4, we take the precise calculations to quantify the summary statistics. The first thing we're going to want to do is summarize our stationary data. This is going to tell us the mean and standard deviations. It's important to only summarize stationary data. That is data where the mean and variability are going to be constant over time. There's no point calculating a mean of a variable that's trending up because the mean is just going to be increasing over time. You can't pin it down. The other thing we want to note is that we have the same number of observations for each of our variables. There's no point in reporting summary statistics if we have different sample periods. And the way that we achieve this is by restricting the sample over which we summarized our data. Here we just said summarize if the time is greater than 1994, but we could also use this tin command if we want to specify a date range. The other thing that we can see is we get a lot of significant digits here. So, 0.587163, that's too many to report. Never report that many in a table or provide that as an answer. Generally, 2 or 3 significant digits is all you're ever going to want to report because guess what? Our data isn't that precise. We don't want to give a false impression. Now that we can see the standard deviation of GDP and inflation, we can see that the standard deviation of GDP is higher than that of inflation. So we are confirming that CPI inflation is less variable than GDP. However, before you are tempted to copy and paste this data, what we can do is just calculate this precisely in Stata just by summarizing the variables individually and then taking the ratio of those two standard deviations. And we can save the standard deviation of that variable just by using this R and then SD command. You can see that we are told that that ratio is actually 0.49. Which means that CPI inflation is about half as volatile as GDP, which confirms what we had seen in the graph. The last thing we're going to want to do is look at the correlations between GDP and inflation. The pwcore command is going to give us the correlation matrix between our variables, and I've ordered the variables in this specific way, giving the lag, the contemporaneous value, and the future value of inflation, and then ordering the variable which we want to take the correlation with last. The reason I did this is because we can just look at this last row of our correlation matrix to see the contemporaneous correlation of GDP with inflation, the correlation of the previous value of CPI with the contemporaneous value of GDP, and the future value of CPI with the contemporaneous value of GDP. Here we can see that the largest correlation is actually between the current value of GDP and the future value of CPI. This means that GDP leads CPI, or another way to say this is that CPI lags GDP. This is really useful to know because it means we can potentially use GDP as a useful predictive index for CPI inflation. So let's now model that. Here, we just have an autoregressive distributed lag model where we're just regressing the current value of CPI inflation on its lag value and the lag value of GDP. And we're restricting our sample to pre-2010 because we're going to use our post-2010 as our out-of-sample forecast evaluation sample. We can see that we've estimated the model with only 63 observations, which isn't very much. However, the R-squared adjusted of the model is about 52%, which is suggesting that about half the CPI variation is explained. We have a pretty large autoregressive coefficient on the lag value of CPI inflation, which is highly significant, and a relatively moderate coefficient on GDP, which is significant at the 5% level. When we test for serial correlation in the residuals, we are unable to reject the null of no serial correlation at any reasonable level of significance. However, we would also want to predict the residuals by predicting and then selecting the option for residuals and then running a varsoc command on those residuals to test for the presence of additional autocorrelation. And here we have a battery of tests, and our information criteria is still telling us that we have at least 5 potential extra autocorrelation in the residuals. One thing we can do to select a model with more autoregressive lags is use the varsoc command on both the CPI inflation and GDP. This is going to assume a bivariate var and is going to regress both CPI and GDP on lag values of itself and provide the information criteria that would suggest the maximum number of lags. While this is pretty generous for the number of lags that would be selected, it is a half-decent starting point. Here we can see that some of the information criteria are telling us that maybe up to 10 lags would be required for both of the variables to capture the autocorrelation. We can whittle that down further by doing hypothesis tests, and the point is to find a parsimonious model that can satisfy both tests for white noise and fail to find significant residual autocorrelation. Once we have that model, we can conduct hypothesis tests on individual parameters or joint parameter testing. Here, we're unable to further whittle down the model because any further restrictions on the parameters are rejected at significant levels. Finally, we can construct an out-of-sample forecast by again rerunning our predict command, but here using the option XB, which is the fitted values. And we're going to fit the values over the out-of-sample forecast evaluation period for post-2010. Once we predict our variable, we can then compare how well our model did in its out-of-sample 1 period ahead forecasting. We can see that our 1 step ahead forecast closely followed the realization of CPI out-of-sample. So now you know how to conduct analysis that is both automated and reproducible. We also know how to visualize the data and to formalize summary statistics. We also managed to construct an out-of-sample forecast. In the next video, we're going to look at Monte Carlo simulations and the issue of the spurious regressions. Make sure to like and subscribe.